So let's see and let's try to understand the working of distance vector routing algorithm with the help of this example. Okay, so here we have three routers, and this is the link cost associated with between each pair of routers. The link cost between x to y is 2. The link cost between y to z is 1. The link cost between x to z is 7. So every node has its own distance vector table, right? And let's try to understand the distance vector table here, that what it represents. So this table of x has rows and columns, where the rows represents the destination. So the rows represents the destination, whereas the column represents the neighbor or via, right? So the column represents what? So the column represents neighbor, okay. So look at the table of x. So what are the different neighbors of x? Yes, y and z. So what are the entries here? Y and z, because y and z are the neighbors of x. And what are the destinations, by the way? Yes, y and z, right? Because these two are also the destinations, possible destinations for x. So this here represent in columns neighbor, via. The rows here represents the destinations, right? So this this table might have looked different if I add another node here, another router here. Let me just assume that here is router T and its cost is 2. So what do you think, where will be the change in this table? In rows or columns? Yes, there will be no change in columns. Why? Because router T is not the direct neighbor of X, but yes, router T is another destination, right? So in columns, we'll have all the neighbors, and in rows, we will have all the destinations. Okay, so, so as per the algorithm, in the initialization step, if a destination is an adjacent node of the source, the cost is known, which is true here. Why? In the case of destination y. Why? Because y is the direct neighbor of x, and this cost is known, being the adjacent node. So this cost is 2. Why? Because it's the direct neighbor. And look at this cost, and also learn how we're gonna read it, right? The cost to reach from x to z via z, right? So this is what, this is the cost, the distance to reach from x to z via z. So what does this mean? That z is the direct neighbor of x, right? The cost to reach from x to z via z. The cost to reach from x to z via z means z is the direct neighbor of x is 7, right? So so we have learned how these two costs are being represented in the table. But what about this cost? How are we gonna read this cost? So this cost is the cost or the distance to reach from x to destination y via neighbor z, right? But this cost has not been, in this initialization step, this cost has not been communicated to x by z. So this cost is infinity to start with, right? So we have no information. Why? Because z has not exchanged this information, that what's the cost to reach from z to y with x. So at the moment, this is infinity. And what do you think? So this cost is infinity, and it is being represented here. And what do you think was the cost to reach from x to z via y? And again, we can write it. I will write it one more time. That is the cost to reach from x to destination z via y. So x to z via y. So what is this cost? This means this is the cost from X to Z via Y, and Y has not, and since we are in the initialization step, Y has not communicated this cost with X. So that's why again it is infinity. So this is the situation in table distance vector table of X in the initialization step. Similarly, we have the table for Y, and what it says, which are the neighbors of Y, X and Z. So in columns we have X and Z, and X and Z are also two destinations, right? And if I assume that there's another router T, so what do you think where we have to change for Y? Yes, we have to add T here as well in the column Y, because T is the neighbor of Y and T is also a destination, so we'll also add T here. Okay, so what do you think was the cost to reach from Y to X via X? Means X being the direct neighbors. What I'm saying is, what is the cost to reach from Y to X via X, right? So means this is the distance to reach from Y to X via X, means X being the direct neighbor. So the cost to reach from Y to X via X is 2, right? We know this Y because it's an adjacent node, so it's known. Similarly, what's the cost to reach from Y to Z via Z? Y to Z via Z being direct neighbor, this cost is 1, right? And what do you think, what's the cost to reach from Y to X via Z? So what I'm saying is Y to X, but via Z. So Z has not communicated any information at the moment, so this cost is not known, so it's infinity. What is the cost to reach from Y to Z via X? Y to Z via X, right? Again, X has not communicated this cost with Y, so it's again infinity, right? So, and obviously, you can notice here that what do you think was the least cost to reach from Y to X? Yes, infinity or 2? 2. So what I've done is I have marked this cost as least cost using this circle. And similarly, we have the table of Z. So what is the least cost to reach from Z to X via X? Z to X via X means X being the direct neighbor of Z. Z to X via X is 7. So adjacent node known. So right. Then what's the cost to reach from Z to Y via Y? Z to Y via Y, again the direct neighbor, the cost is known, 1. And what do you think was the cost to reach from Z to X via Y? Z to X via Y. So Y has not communicated any information with Z, so this cost is not known, infinity. And similarly, the cost to reach from Z to Y via X, again X has not communicated this cost with Z, it's infinity. So in the last step of initialization phase, what we do basically is once we have known the cost to reach the other destination, for example, in the case of this Y and Z, so what Y will do, Y will send update messages to its neighbor. So Y will send update messages to Z and X. Similarly, Z will send update messages to X and, yes, you're right, Y. And similarly, X will send update messages to Y and Z, right? And what X has to tell, for example, what Y and Z has to tell, these least cost to reach to certain destinations, right? So let me go back and look at the initialization step of the algorithm. So, and the initialization step for all adjacent nodes, if V is the direct neighbor of X, so this means the cost is known, that is the cost to reach from a node X to destination V, where V is the direct neighbor. And if it is not known, the cost is infinity, okay? And once we have this initial cost, so what we do basically, we share this minimum cost with each other to update our tables, right? So what will happen if we look at this? What will be the message that X will be getting, right? So see, what we are doing here is that in the initialization step, we are getting this cost for, this update messages from Y and Z. So X will receive update messages from, Y and Z. So what is the update message from Y? What do you think? So what Y has to tell to X? So Y has two costs here. The cost one is to reach from Y to X. Probably X won't be interested in this cost, right? So what about the second cost here? The cost to reach from Y to Z. The cost to reach from Y to Z is 1. So this is a message from the neighbor Y, and we will update this table of X using this message. So this is this message here, right? So how, when we will, and using this equation, we will update the table of X. So what it says is the cost to reach from X to Z via Y. So this via Y here is telling me that the update message is coming from the Y, right? To reach destination Z. So what is the cost to reach from Y to Z? It's 1, right? So we'll do first, we'll calculate the cost to reach from itself to Y. So if we look at the table, what do you think was the cost to reach from X to Y? Yes, 2. That's because Y is the direct neighbor of X, and we have this cost in the table as well. So it's 2. And what's the minimum cost from any of the neighbor of Y to reach the destination Z, right? So if we look at this update from here, this cost is 1. So the cost to reach from Y to Z via Z, because Z here is the direct neighbor. So if I modify this equation, this would be, and in fact, it would be this, right? So the cost to reach from Y to Z via Z, right? So Y to Z via Z, it's there in the table, it's 1. So the cost to reach from X to Y is 2, and the cost to reach from Y to Z is 1. So this cost is 3, right? So we are talking about this cost, which was initially what? Infinity. Okay, so this is the cost to reach from X to Z via Y, right? So neighbor Y. What's the cost? 1. So what's the cost to reach from X to Y? 2. So 1 plus 2, as we have seen in this equation, it's 3. So this is the new least cost, by the way. Previously, the least cost was 7. Now we have a new least cost via neighbor Y. So if I want to send data from X to Z, so the least cost is from X to Y via X to Z via Y, right? So we have the new least cost, and I have marked here the new least cost. And similarly, Z is also sending a message, update message to a router X. And what Z has to send, if you look at the table of Z, yes, the first entry is the cost to reach from Z to X via X. Obviously, X won't be interested because Z is the direct neighbor of X. But look at this second information here. The cost to reach from Z to Y via Y, right? So it sends this information to X. Look, if you want to reach from me to Y, the cost is 1. And what X does is, it says, okay, fine. What's the cost to reach to my neighbor Z? 7. So 7 plus 1 is 8. So the cost to reach from X to destination Y via Z. So I'm talking about this cost. The cost to reach from X to Y via Z. Okay, which was previously what? Infinity. So what I have to do for in order to calculate it? So first I will calculate the cost to reach from X to the neighbor Z, and then whatever is the update that is being shared by Z, which is the cost to reach from Z to Y via Y. So Z to Y via Y, which is 1. Okay, so 7 plus 1 is 8. So we have a cost update here, but obviously this is not the least cost, right? So still 2 is the least cost, right? 2 is less than 8, so that's why it's the least cost. And similarly, in order to calculate the table of y, y will receive updates from x and z here, right? And z, for the calculation of z's table, z will receive updates from x and y, right? And we can again see the situation in the table of y and z. So look at the table of y. So this entry was already there, 2 and 1. So what has happened here? So this is the cost reached from y to x via z. So this means I can understand that this message is this least cost change is because of the message update message from z. So what z has to tell y? So again we look at the table of z here. So z has two costs. The cost reached from z to y via y being the direct neighbor. So obviously y won't be interested in this cost. But look at this cost. The cost reached from z to x, which is 7. So z informs y that the cost reached from me to x is 7. So it says, okay, fine. So the cost to reach from you know my neighbor z is 1, and the cost to reach from z to x is 7. So the cost to reach from y to x via z is 8. So the cost to reach from y to x via z is 8. But this is not the least cost. Obviously, there is an improvement because previously this cost was infinity. We have updated a number, but this is not the least cost. Similarly, look at this cost. The cost to reach from y to z via x. This means this update message is coming from x. So what we have in the table of x, the cost to reach from x to y, which is 2. Obviously, y won't be interested in this cost. And what is the second cost? The cost to reach from x to z via z, which is 7. So what x is telling y, that if you want to reach from me to z, the cost is 7. So what y calculates is that the cost to reach its neighbor x is 2 plus the cost that x is advertising 7. So this means if y takes this path to reach the destination, the cost is 9. So the cost to reach from y to z via x, via means through neighbor x, the cost is 9. So using the same equation that we have discussed in the previous slide, we will calculate this cost. And obviously, this is again not the least cost, okay? Because 1 is the least cost. And what is happening here in the table of z? So in the table of z, here we have this update, that is the cost reached from z to x via y. So this means this message is coming from y. So what's the situation in y? So there are two entries here. The cost reached from y to z via z means z being the direct neighbor, and the cost reached from y to, and z won't be interested in this value obviously, and the cost reached from y to x via x means 2. So what y is telling z, that if you want to reach from me to x, the cost is 2. And what's the cost from z to y? 1. So 1 plus the cost from y to x to 3. So we have here this cost 3. That is the cost reached from z to x via y. And y tells the cost reached from y to x is 2. And the cost reached from z to y is 1. So 1 plus 2 is 3. Right? So here we have 3, and it's also the least cost, right? Because it's less than 7. And similarly, look at this value here. The cost reached from z to y via x. So this means this update message is coming from x. So what x has to tell to z? The cost reached from x to z via z, 7. Obviously, z won't be interested in this cost. And the next is telling z that the cost reached from x to y is 2. Right? So what's the cost to reach from z to x? 7. So 7 plus 2 is 9. So here we have this cost 9. Okay. So then in the loop, we wait for the least cost to change to a destination. And yes, this is the case here. What do you think? Uh, which router will send the update message now? Is there any change here in the table of Y? No. I mean, in terms of the least cost, the least cost is still 2 to reach destination uh, X, and the least cost is still 1 to reach destination Z. But do we have a change here in X in terms of least cost? Yes, there is a change here. The least cost has changed from 7 to 3. So this means X will send update messages to Y and to its neighbor, to Y and Z. Okay. Is there any least cost change in the table of Z? Yes, there's a least cost change here. The least cost has changed from to reach from X to reach from Z to X has changed from 7 to 3. So this means Z will send update messages to its neighbor, Y and X and Y, but there won't be any update messages from Y because the least cost has not changed, right? So again, if I go back to the algorithm and see that in the loop, we wait for two things to happen. Number one, to see a link cost change to a neighbor V, but this is not the case that we are discussing at the moment. But yes, there is an update from neighbor V to some destinations, right? So if there is a change, what we'll do, we'll calculate the updated cost in each table using this equation, and if um, uh, so we're using this equation, and if there is the new cost is minimum, so we're gonna again re-notify to all the neighbors. Okay, so so what do you think? So this means X will receive update messages from, yes, Z only, right? Because Y will not send any update message. So what is the update message that Z has to communicate to X? So look at this change, right? Z has to inform X that the cost to reach from Z to X has changed from 7 to 3. So do you think, will there be any change in the table of X? That Z is telling X that its cost to reach X has changed? No change, right? So it will bring no change at X. Okay, so there will be no change here. And similarly, what message X has to inform to Z? What's the change here? So X has to inform Z that the cost to reach from X to Z has changed from 7 to 3. So what do you think? Will we have any improvement here in the table of Z? No. So no change in the table of Z. But there is an interesting change here in the table of Y that we have to understand, right? So let's look at the table of, so you can see there's no change in the table of X, it's the same, right? There's no change in the table of Z, it's also the same, no improvement here. And by the way, there is also no change in the table of Y in terms of the least cost. So least cost is still the same, right? Just as so. But this is important here. So we have some new values here that I want to discuss with you, and I want you to pay attention, understand it, right? So because this will help us to understand the problem, the shortcoming of distance vector algorithm. Okay, so what is this cost? So this means this is the cost to reach from Y to X via Z. Okay, so this means this is the cost, by the way, that I'm talking at the moment with you, is the cost to reach from Y to X via Z. So this means this update, this change is because of the message from Z. So what is the message from Z? What was here with Z to communicate? Yes, the link cost to reach from Z to X is 3. So Z is telling Y that the cost to reach from Z to Y has changed from 7 to 3. And Y says, okay, fine. What is the cost to reach from me to Z? 1. So 1 plus 3 is 4. So we can see a 4 here. But there is a problem with this path or with this cost. It involves loop. And loops are not allowed in networks. Remember, loop is not allowed in networks. And what do you mean by loops? Means a packet should not visit a router more than once, right? And if you focus on this path 4, what is this path, right? So this Z is telling Y that the cost to reach from Z to X has changed to 3, right? And the cost to reach from Y to Z is 1. So 1 plus 3 is 4. So what happens basically is, if I take this path, by the way, this path is not taken, but this can create a problem. We'll see in a minute how, right? But I just want to make you understand that how it creates a loop here. So this means if this path is selected by somehow, this means what? This means that Y will first send a packet to Z, right? And look at the Z's least cost to X. Let's go to the Z. And what is the least cost of Z to X? The cost to reach from Z to X via, and this least cost is via Y. So this means Z will again send this message to Y, and via Y it will go to destination X. So this means there is a loop here. This packet is visiting Y more than once, creating a loop, right? So this path involves loop. And this will never be selected, by the way, but this can create problem in the convergence time of the algorithm, means the number of iterations that an algorithm has to do in order to be in a stable state. We'll see in a minute how. And similarly, look at this path also, this path. This is the path to reach from Y to Z via X, right? So this means the message is from Y. The change is because of the message from Y, and so from the change is because of the message from X. So what is the message from X? What X has to tell to Y? Yes, X is telling Y that this least cost has changed to 3. So X is telling Y that the cost to reach Z has changed to 3. So Y says, okay, fine, the cost to reach from me to X is 2, and X is advertising the cost to reach Z is 3. So this cost is 5, which is here, right? This again involves a loop. If this path is selected, right, this means what? It means Y will first send message to X, and then we go to X and we see the cost to reach from X to Z is 3, which is the shortest cost via Y. So this means again, if Y selects this path, Y will first send this message to X, and X will again send this message to Z via Y, and again there is a loop here at Y, right? So again we have a loop here. So this means this can create problem for us in terms of the convergence, the number of iterations required for the convergence of the algorithm. This problem needs to be taken care of. That we'll see in a minute how we can cater this problem. So allow me to go back to this algorithm here so that see if it's clear to us or not. So in this loop, node will wait for two things: either a link cost has changed to a neighbor, or there is an update from a neighbor with respect to some destination B. So we have covered this part, right? So we have covered this this part, and if there is a link cost change by D, so we'll calculate the new cost, and else if we receive an update with respect to some destination Y that we have seen in the example, so we will again calculate the new cost as we discussed, and if the new cost is the least cost, so we have to communicate this least cost to with all our neighbors. And if this new cost is not the least cost, which was the case with Y, so there won't be any update messages for the neighbors, and we'll again remain in this loop waiting for either a link cost change or an update with respect to from a neighbor with respect to a destination, say V.